lecture. Ma'am will be taking totally 5 days. So in our second day, we'll ask Nivedita ma'am to start. Over to you, ma'am.
Yes. Thank you, sir.
Yes.
Good afternoon, everyone. So let us start today's session. I hope it is visible. Yes.
Yes, ma'am.
Yes. Okay.
Yeah.
So today is a lecture 2 for QT02. And just a quick recap on what we actually have seen in yesterday's class is basically we learnt about the pitfalls of the classical computing with respect to the time, space, inability to like simulate any natural system, as well as the kind of like the complexity that was also a factor. And so we have seen after that that what actually gives quantum these advantage, quantum computing these advantage. And there we have seen all these principles, at least the definition of them. We have looked into the superposition, not mathematically but at least conceptually, where it is the ability to be present in multiple states together, or in easy words it is to encode multiple possibilities simultaneously and to be able to compute all of them simultaneously. This is something that superposition offers. And we also have understood that superposition is that only principle that enables quantum to have that kind of a speed up or advantage or supremacy that we talk about. So this is through superposition. Then we have seen entanglement, where we talked about it, that it is a weird property, bizarre property of a quantum mechanical body, where we believe that two qubits, they can be entangled, meaning they can share certain sort of relationship between them. Either that can be a positive correlation, that is some positive, say directly proportional relationship, or it can be some inverse proportional or anti-correlation as well. So out of that entangled pair, one qubit can be placed at both the sender as well as receiver end. And quantum communication is that field, and cryptography, where basically primarily this entanglement concept is used. Okay. Third one, we have seen the interference, where it will just like the river water or any water body, we can see that or in a pond basically, where two waves they can be created. So if they're in alignment with each other, then that will lead to a constructive interference, that is a bigger wave. So in terms of computing, it means that number of quantum states will be increasing. That is a constructive one. And another interference thing we have seen is the destructive interference, right? Where we have seen that if two waves somehow cancel out each other, that is reduction of the number of quantum states by increasing the probabilities of the resultant states. Mathematically, we have not seen it. Maybe today we will be exploring the examples of this. Okay. Then next one, and where it is used in everywhere where we actually want to get the desired answer from out of a superposed state. So we use this principle of interference just to cancel out or to amplify a few states. But there is no fixed operator for that. There are a set of operators or a set of principles or logic that you have to define in order to get the interference. And it depends on what? It depends on your specific application and the kind of output you want to obtain. Next one is the no cloning theorem. It is not any kind of technology, it is an inherent property of a quantum mechanical body that you cannot clone any quantum state if it is an arbitrary quantum state. So that was a theory, and we believe that it is like there is no machine that can clone, or that can copy, or that can xerox a particular state that you have. Today maybe we again will look into the mathematics of no cloning as well. So it is where it is used primarily, the concept is used in maybe just any kind of a cybersecurity threat detection or eavesdropping detection, kind of that. So mostly in cryptography and cybersecurity, the no cloning theorem are primarily used. Okay. Next one is a decoherence. So it is not any as such advantage that quantum offers, rather it is a disadvantage. Where it says that the quantum systems are basically very fragile in nature. So they lose the quantum property or that coherence if they are kept as it is for a longer period of time. Now this can take place because of a lot of reasons, right? There can be some coupling error. The qubits itself can be noisy. The qubit interaction, okay, that interaction can also cause some coupling effect. Maybe if like two interacting qubits, if they are not very close or they are very far apart from each other, then during that time it will actually take to interact, or that algorithm to take place between these two qubits, if that is also very high, then that can also result in decoherence. So there are several solutions for decoherence. One of the solution are algorithm level, where you try to come up with some very smart algorithm so that the interaction time gets minimal, or interacting qubits or neighboring qubits can be placed at a minimum distance than each other. Or it can be at the physical level, where you might be thinking of controlling the environment in a better way, so that the environmental loss or environmental noise cannot affect the quantum system. Or it can happen in the architecture level, where whenever you will be building the qubits or the quantum gates, so you have to be using some error correcting qubits. Okay. Or maybe some different physical architecture itself you have to rely on. Maybe superconducting qubits actually yield to, say, x unit of decoherence, but maybe trapped ion architecture or maybe some photonic architecture, if you use that in order to make your quantum gates or your qubits, that might be more, like, say, application friendly in terms of less decoherence that they are causing. So it's all about a lot of like hardware and architecture dependent, and a few of the algorithm level optimization as well. It depends on all these factors. But decoherence is a problem. It is not something that we want, but we have to deal with it. So with all these things, now we will start today's class, where first I will be talking about this thing. So the classical solution. Now this solution means it can be either optimization, it can be chemistry, it can be AIML, it can be some other things, anything. So this is an in general kind of a difference between the classical computing solution versus the quantum computing solutions. So where the first one is the underlying approach that we use, the model of computation, whatever you say. So the classical one uses some systematic or mathematical model of computation. That is the algorithm. Okay. And quantum version, on the contrary, relies on some physical model of computation, right? Which is, of course, not classical physics. They are like more or less quantum physics or quantum mechanics, which we will look into today. But it's a physical model, the underlying approach. Next one is the type of computing that they use. So we also mentioned about this thing yesterday, that classical offers, or classical does not offer, non-deterministic way of inferencing, where from a particular point we can visit multiple possibilities together. This is non-determinism, but classical does not offer that. So here inferencing is very much of a one-on-one mapping kind of. So it's a deterministic inferencing approach. On the contrary, quantum uses a probabilistic reasoning, meaning, say it's like from a particular point I can go to three different nodes, and each of them, say for example, I have a 1/3 amount of probability. So if this state is represented by, say, q0, this is q1 and this is q2 and this is q, so my q is a possibility, like Q holds a possibility to reach to Q0, Q1 and Q2, all three of them. But definitely the probability, unlike classical, where I can say directly go to Q0 only with 1, that is 100% probability. This was in case of a classical, but here for quantum it is 33.33% probability to reach to any of the vertices or nodes or options. So here the reasoning type is probabilistic, not the deterministic. Deterministic means 100%. Okay. Third one is the computing power, where classical is basically in the polynomial of input size. That is, it is f of n generally. But unlike that, here the power is in 2 to the power n. And we know the example of 5 fingers that we were talking about. So in classical with 5 fingers, the maximum that we can take is only one combination of size 5, say 01001, right? But unlike classical, in quantum, it is basically with 5 fingers or 5 qubits, we can actually represent this thing like 2 into 2 into 2 into 2 into 2. That is 2 to the power 5. So this is the computing power that quantum offers, right? Where 5 is the number of qubits and 2 to the power 5, 32 are the total number of quantum states. Okay. Next one is the sampling error. Mostly it is associated with machine learning. So sampling error is the error that we have when we pick up a sample from a bigger population, right? So for a lot of decision making things or statistical approaches, we use this particular technique. So of course, while picking up a particular sample, if that is biased to a particular, say anything, say a ethnicity or gender, or say a particular kind of a historical record, if it is biased, then this particular thing can happen in case of a classical solution. And why this happens? Because of the lack of computational power. So we do not know a particular data set or as chosen as a sample that can be little skewed towards a particular biased outcome. So there can be an imbalance between the sample and population. And mostly this is visible for machine learning applications. On the contrary, in quantum, the decisions are unbiased because of the less error probability during sampling. And why? Because if we use a quantum SID or a quantum random number to choose during the picking the sample from the population, because of that randomness of the quantum SID, the sampling error has very less chance to take place, or it will be reduced. And for the same reason, as an implication of that, the accuracy and precision for a classical solution, that if it can be optimization, it can be machine learning, it can be anything, that is less. And on the contrary, for quantum, it is more. But now here you might be asking a question that, say for example, you got some data set for the machine learning and you want to implement it in a quantum, like a QML application. And if you feed it to a very powerful machine learning algorithm versus the quantum one, does it really guarantee that it will be giving you that kind of an accuracy or precision? Or if it does not give it to you, does it mean that quantum does not offer that speed up? So you can be having this practical question. So the answer to these are several points, are the caveats that you have to understand here. First is what algorithm you are using for quantum, how strongly you are encoding it, or are you partially encoding a few features. So your encoding or your superposition will actually yield to the speed up. This is the point number one. Point number two is how complex your data set is. Because right now, classical is very powerful, or it's almost like fully set, all the hardware and all, they are very matured, which is not the case for quantum. So maybe for a simple data set, or maybe the your quantum machine learning algorithm till now discovered, or the quantum hardware or the qubit specifications that you are using or will be using, that may be only suited for a smaller data set. And the similar thing, similar kind of a this flavor you can get if you go to the quantum natural language processing, QNLP, or all those stuff, where mostly it is kind of the quantum AI, that particular field I'm talking about. So there you can see this thing, that accuracy and precision wise, you might see some kind of a discrepancy between what you theoretically have learned and what you will be actually getting there, in terms of number of epochs, in terms of the time taken, in terms of all these things. But for that, you have to remember that we are claiming everything for the FTQC, or the fault tolerant era. If you ask right now we are standing in a noisy intermediate scale quantum era, which is a NISQ era. So you cannot expect it to be 100% noiseless. So two things you can do here. First is, either you can go for building the noisy systems where very strategically you have to pick up the problems and map it in terms of a hybrid mode to classical and quantum. And then maybe a particular subroutine you can try to optimize in the quantum setting. Or second solution can be, you have to wait, or maybe right now you are building some prototype in the FTQC or the fault tolerant era, where you believe that the qubits will be less noisy. So you will be assuming things in that way. There will not be very encoding challenges there and all those things. So under a certain consideration, and you have to like fully migrate or fully think of migrating to a quantum solution for the FTQC or fault tolerant era, which is not currently the situation. But very soon it will be the situation as per all the like predictions and commitments by the big giants. Right? So I hope this is clear. Now on that note, so what we will be looking into it, we will be looking a little of the physics angle, which is a theoretical physics kind of that, classical physics and the introduction. We will understand at least the ground, or what are the very like dominant like theorems and all that we should be knowing for the theoretical purpose. Then we will slowly set the ground that why we need quantum mechanics, and followed by that we will enter into the all the vector algebra and everything that we actually made a commitment to be doing today. Okay, so all the mathematics will come post that. So first of all, you know that the classical physics, the Newtonian physics and all, that explains our everyday macroscopic phenomena. But whenever it has to enter into the microscopic or atomic scale, it collapses. And there were a lot of theories for that. Now I'm not from the very like good physics background, so I will just make a good touch up of that. Then we will enter into the quantum mechanics. So the first one was the ultraviolet catastrophe and black body radiation. Now, there was a theory by Rayleigh Jeans, that as per his prediction, the black body radiation should emit infinite energy at very high frequency. And as per Planck's breakthrough, energy was not continuous, it was quantized. And that was the very like say initial idea behind the term quantum, because quantum means it's a like a quanta, it comes from the word quanta, which means packets of energy. So here we believe that energy is not continuous, rather it is quantized, so kind of absorbed or emitted in discrete packets. So this is the equation, E is equals to h mu, where this is the radiation frequency in hertz, h is the Planck's constant, which is this particular value, joule second, and E is the energy of one quantum in joules. You know, joules is the SI unit of energy and all. So the key insight of this Planck's breakthrough was that light behaves like individual energy quanta, which we also refer as photons, not just waves. Okay, so here we are committing as the like quantized form of energy. In easy words, this is the kind of argument. Next was the photoelectric effect, where the classical prediction was that increasing the light intensity should eject more electrons regardless of the frequency. So if we increase the intensity, there will be more ejection of the number of electrons. But Einstein later actually discovered that electrons are only ejected if the light frequency exceeds a particular threshold, and it is not a dependent factor of the on the intensity. So the conclusion was light is not just a wave, it behaves as particles carrying some energy. E is equals to h mu. Okay. Third one was to prove that light has certain momentum. So classical physics said that waves have no momentum. But yet experiments showed that the extra photons transferring energy to the electrons, they actually, if they're transferring something, then that has to have certain sort of like mass into velocity kind of thing. So light has momentum as well, like the tiny billiard balls. And mathematically, this is the formula for this, that momentum is equals to this Planck's constant divided by the wavelength lambda. So the takeaway from this was light behaves like a particle with momentum, contradicting the classical wave only kind of explanation where we believed it has no momentum. And the last one was the double slit experiment, where expectation was initially that electrons, being a particle, should pass through one slit or the other, forming two bands. Right? But during experimentation, what reality they had faced is there is a mysterious interference pattern that is emerging. Something like this they can see. So instead of direct two bands, they actually have seen something like this. And it is also like this. Say at some point it was like this, then some bigger band, then maybe a little more bigger band, then again some small. So likewise, so in that plane where all the the reflections that they were seeing, okay, the outcome, their visible outcome were like there, they have seen that there are a effect of interference in that. And of course you can understand that the very deeper kind of interference patterns were seen where light actually exhibited constructive interference, and where it was very like minimal, instead of the normal band size, there they were exhibiting the destructive interference. So that actually proved the interference property of light as well through the double slit experiment. And also because of the de Broglie like hypothesis that there is a which came into picture, that there is a wave as well as a particle nature of light. So it is basically both. And later, Schrodinger equation and all, it actually governed this principle and showed the accordingly the proof and all, where it has a continuous property as well as the discrete property. Okay, and this is the same wave-like behavior of that quantum or say photon, which gives us the probabilistic inferencing model that we talked about. We believe that since it is in a wave form, so it can actually exhibit in simultaneous possibilities together because it's ultimately wave. So wave at a particular point maybe has a 30% probability, at but some point it can have a 20%, in some point it can have remaining 50%. Likewise, it can exhibit or it can exist in multiple probabilities together because of the wave property of light. Okay. Now, a little kind of say explanation for all these things. So imagine a metal rod heated in a furnace. So first it will glow red, then it will become orange, then at extreme high temperature it will shine in a blue white colored type. But why does it change color with the temperature? So scientists tried to explain this using the classical physics, which initially they tried. They believed that a heated object should emit radiation continuously at all frequencies. But if that is the case, then the actually measured energy emitted at different wavelengths, it does not match with the classical predictions with the amount of energy that it should emit. And the formula called the Rayleigh-Jeans law predicted that as wavelength decreased, the emitted energy would keep increasing indefinitely. And this meant that ultraviolet light should have infinite energy, which was unrealistic. As you can see in the outcome, it is changing color, so it's not exactly the same. So this incorrect prediction was called the ultraviolet catastrophe. So here these are all the real experiments that were conducted which contradicts with the classical physics that or the Newtonian physics behind backing up that all those principles. So it's a contradiction. Okay. So it showed that the energy is quantized. The first one that we talked about. What was the second one? The that kind of thing that yes, okay. Yes. So after this, the Planck's hypothesis was the solution for that, which actually proved that the energy is quantized, where he showed that instead of energy being emitted in a very smooth or continuous manner, it is getting emitted in a discrete, say, packets form, which we called as a quantum. So the higher the frequency of light, the larger is the energy of each quantum. This idea meant that a very high frequency energy emission was limited. So the ultraviolet catastrophe, that it has an infinite frequency it will be emitting, this was wrong. So that catastrophe, that idea, which was backed up by classical physics, can be avoided. So though Planck introduced this concept as a mere mathematical trick, but it led to the foundation of quantum mechanics, because quantum itself start with this kind of that quanta, okay, or packets of energy theory. So it believed now that understanding that nature isn't continuous at the smallest scale, it is quantized. Right? Later, it was also revealed that it is quantized as well as continuous. So basically, it is continuous, but whenever we try to measure it, it becomes quantized. That was the original outcome that we will be getting. Right? But this actual theory establishes that the nature isn't continuous at small scale, it is rather quantized. There is certain sort of a quantized packets of energy that exist in nature. Next was light is made up of particles, the photoelectric effect and Einstein's this thing. So here actually they have seen that the experiment was, say, say whenever some light shone on a metal surface, it ejected tiny particles or electrons. So that is some kind of a photoelectric effect, and we all have seen, or I guess we have experienced it. Some tiny particle like thing we can actually see in a particular light form. So that is the weird part. The brighter light or the more intense light didn't always eject electrons. Only light of a certain color or certain frequency worked, even if it is dim. And we all have seen these kind of things. At a particular frequency itself, we can see some of the like tiny particle like thing which like seems like a photoelectric effect. So increasing the brightness just increase the number of electrons, but does not increase the amount of energy that they have. And classical physics had no explanation for this. According to the wave theory of light, any bright enough light should eventually knock off electrons, but that didn't happen. As an effect of that, it was the Einstein's radical idea where he showed that light isn't just a wave, it also acts as a tiny particles or like a photon. So light is made up of particles. So initially it was that light is actually in form of quantized form of energy. This was that light is made up of particles. Okay, and each photon and each of those light particle, which is a tiny particle, they are called a photon, and each photon carries a fixed amount of energy. So if the energy is enough to overcome the bond holding the electrons in the metal, that electron will get ejected, and if the photon's energy is too low, then the electrons are not emitted no matter how bright the light is. So just like the nucleus of the atom that we know, only with help of some energy it can actually go to the ground state, to the excited state, E1, E2, E3, and likewise. Okay, and this proved that light behaves as both a wave and a particle, opening the door to the wave particle duality of quantum mechanics, which was proposed by de Broglie. Okay, and the real life application was this principle is used in solar panel where sunlight knocks electrons loose to generate the electricity. Okay, then the next was the Compton scattering of light. So imagine you are playing billiards. When one ball strikes another, the first one loses energy and the second one moves away. Could light also behave like that? So in 1923, Crompton performed an experiment where he shone X-rays onto electrons. And he found that after the X-ray hit the electrons, the scattered X-rays had a lower energy than before. So that definitely means there is a velocity kind of equation. As mass was there, but there is certain sort of velocity thing. But classical physics said light waves should not lose energy just by scattering, but it did. So the solution was, so this experiment confirmed that Einstein's idea that light is made up of some particles is true. And when a photon collides with an electron, it loses energy and changes its direction, just like the 2 billion balls colliding with each other. This showed that photons do not just carry energy, but also they have certain momentum. So, despite having no mass, and all these things are important for us to understand because of that. What are the properties of all the photons whenever we will be building up some qubits? So what are all the things that we have to consider? The phase, the angular momentum, the like each and every rotation or that angle with respect to the x, y, and z plane, they will actually maybe like point to different information. So likewise also we can encode some information. So all these things are very important for in order to understand that, and each confirm a different kind of properties of quantum particles or photons. So this was for the momentum property of photons. And the next one was the double slit experiment, or that is the birth of the wave particle duality. I just mentioned that imagine shooting tiny bullets through two slits in a wall. So you should expect to see two strips on the screen behind the slits. But actually, what you can see is kind of that interference, kind of fringes you can see. So they will be creating some interference pattern of many bands because waves overlap and amplify, that is in alignment, or cancel, that is not in alignment with each other. And things got weird when scientists repeated the experiments with electrons. So this was something that they could observe. So this also says that particle, they behave as waves and their behavior changes when it is observed. Then you can at some point you can see some constructive, at some point you can see some destructive. That is a like a dense pattern, say, or a very sparse pattern whenever it is observed. But before you observe, the particles will behave as a waves. So this is the quantum mystery, that electrons act like waves. So when electrons were fired one by one through the slit, they still form an interference pattern, as if each electron somehow passed through both the slits at once and interfered with itself. And on the detector, they can see that when they place the detector, that to see that where slit each electron went through, the interference pattern disappeared. Right? That also says that we do not have a control during observation on what was the earlier condition. We can get any different kind of an observation if we try to somehow tamper the quantum particles, right? And the electrons started behaving like tiny bullets again, as if they know that they were being watched. So this is the observation weirdness that we have in quantum physics. And real life application, this is the same thing that we were talking about, because of no cloning theorem and this thing, the measurement kind of like abstraction that we have during observation of that particular quantum state. See, because of these two things, actually the man in the middle attack or those kind of security threats, they can be detected, because a quantum property itself that will be lost if you try to tamper the system, or if you try to tamper the system and if you measure it and then try to create it, then that is also not possible because of no cloning theorem. So now that you know that there are several things, so what are all the observations that we have seen? So in easy words, we have seen that energy is in certain form of quantized. Then we have seen that light is also made up of some particles. Then we have seen there is a photoelectric effect of light. So there is a particle effect of light as well. And then we also have seen that it behaves like a waveform as well. So for centuries, the classical physics developed by Newton and that Maxwell thing, refined by Maxwell, seem to explain everything. But whenever it is in the macroscopic world or the atomic world, they discovered the phenomena that the classical physics couldn't explain. The way a quantum world, their bizarre properties, they work. Then this is the point where the quantum physics or the quantum mechanics that started evolving, where we entirely in a different light altogether, we looked into the behavior of photons. We tried to understand the like we now know that they have some momentum, they are either wave or some particle. Whenever they are to be measured, they lose their property. Whenever you try to observe a superposed state, you do not have a control on what you can observe. So it's some way different, right? So from all these things, now it will enter into that particular. See, now we are in a point where there are a few. What are the pitfalls for classical physics we have seen? What are the pitfalls of classical computing we have seen in yesterday's class? We understood that there is a requirement to enter into quantum like computing as well as quantum mechanics. All these things now we know by today's class and yesterday's class. Now we are in a point where we now want that how we can actually make use of these quantum mechanical principles through something that we will be doing in the classical world only, but we will be able to take advantage of their properties. Now whenever we have to do that, though it's physics, but we cannot really do anything in the physical level. That is not possible. So how to realize that? So how to realize that what will happen in the real quantum world of this particular particle, which is a quantum particle? For this realization, we discovered a new field which we called a quantum computing. So quantum mechanics was there, all these principles, all the mathematics was there. Now we want to actually make use of these quantum mechanical principles in our particular problem area or in our particular computing language, right? So the quantum computing is that field of computing that through some mathematical realization or through some mathematical representation or computation is able to map and manipulate the quantum mechanical postulates in computing paradigm. Clear? Now, since we know till this part, we will enter into this. So quantum physics, basically, it is everything in form of a wave function. So here, every object we can describe in quantum physics in form of a wave function. And every wave function has several consequences. What are the consequences? They can exhibit superposition. We know what is superposition now. They exhibit certain sort of entanglement. They exhibit Heisenberg's uncertainty principle as well, that the position and momentum simultaneously cannot predict. The position versus momentum dilemma that we have. Then the energy quantization by the Planck's law and all, and a few other like principles what we have seen today, as well as quantum tunneling. What is quantum tunneling? So quantum tunneling is basically where we believe, because we also believe that quantum can exhibit both in a wave form as well as a particle form. So we believe that if we are, say, in this position, since it is quantum, so it is not like a particular point. So it is kind of something like that. I'm just drawing a sinusoidal wave, but it can be anything. It can be any wave, where maybe at this point I am with a particular probability P1. At this point I am at a particular probability P2. So within this time frame, I am in multiple probability of occurrence I have to exist. Now, this particular theory is very much useful in this thing where we are stuck in any optimization problem, we are stuck with the local optima. So we call it like this. Say for example, right now we want to build up a solution where we want to get the best minima or the global minima. Right? For that, say it is kind of that. Say just a kind of a, say, mountain or hill like structure have drawn. So when you are in this point, whenever you are in this point, say, you will see, say you are doing in a classical computing, okay, so you will be stuck here because at every point if you have taken, then this is the local minimum point, and here also it is like maximum than this point, right? So now this, you will assume that this is the best one, best solution. But if you say little, do a little exploration further, then you will see you will be getting this point which is not best than this one. So this is still the best, but say this point, this is a little better than this. Say I have now picked up this one, say this is my best one, this is at time t1, t2 was actually bad, I'll not take it. Next solution, say, is best one is t at time t2 or t3. Now t3 is now the best one. So at point T3, I maximum maybe, if consider, just consider I have that information of T1. So I'll be able to compare these two. And what I will assume that, okay, T3 is the best one and I will converge here. But is this convergence the real convergence? or as it should be like? No. So this is a local convergence. And even I will not even reach to T3 because I will be stuck at T1 itself, though there is a better solution at T3. And also, this is also not better. Actually, the best one is at T4. But in this particular kind of optimization problems where we actually try to calculate the lowest energy, we often stuck at the locally based solution because the classical physics and this particular thing is true, or this particular technology is called as simulated annealing. So on the contrary, there was a quantum analog of this simulated annealing. Consider the same thing. Just consider the same thing. Say I'm just drawing till this. So whenever I will be in this position, in quantum, we will believe that since I can be in this position with a probability P1 and in this position with the probability say P2. But I will exist simultaneously at both the points P1 and P2. It's not only P1. Why? Because in quantum, I can actually as if tunnel through. I can tunnel through at all the possibilities that rely in this particular, say, height or that particular level. So in quantum encoding, it has to be in a way where we can be in both the positions P1 and P2 with a certain probability. Maybe they are not 100%, maybe it is 50% and 50%, but we can exist. Now, whenever we are in P2, if we can reside in both P1 and P2, that means, say, consider now I am in P2. That means whenever I am here, I can have a look on this thing. So I will be having an access of this one. And whenever I will be having an access of this one, I will also be able to get at this point. Whenever I am in this point, because I have again tunneled through, so I can have a look on this one. So the best one now I will be getting. So this is the best solution or the global minima, also known as the global convergence. And this property of a quantum particle to tunnel through one point to another, that is to exist in a probabilistic model, in a waveform model, is known as quantum tunneling. So it is basically the quantum analog of the classical simulated annealing. Okay. Now let me just go back here. So quantum tunneling was another phenomena, as I just have said, the wave. They can exist at both the positions with just the differing probability. And all these are consequences of the wave function, which is nothing but an object in a quantum physical world. Now, that particular wave function can be a time dependent wave function as well as a time independent wave function. We will look into those things later. But assuming they are just a wave function, which is an object in quantum setup, on measurement, if you now measure it through some measure gate, you will be getting some particles which are, because it follows the wave particle duality, and I just have said that wave function is a continuous form and they exist in that way, but whenever you are measuring it, so it will now be discrete in form of packets of energy, which is known as particles or photons. So this is the particles because of the wave particle duality plus some mystery. What is the mystery? The mystery is the measurement problem that we have. Now, what is the measurement problem? Problem with quantum measurement is here the outcome are not certain, that is not fixed. What you will be getting at the next timestamp, that is not fixed, that is not certain. You can get any of the outcome. And also the order is also not fixed. You cannot fix the order in which you will be getting the outcome. Say, for example, you are supposed to get the outcome, or you want to get the outcome in form of, like, first time I should be getting quantum state 1, then 2, then 3, then 4, then 5. Okay. But maybe whenever you are measuring it, maybe in the first hand you will be getting 5. So whether you will be getting 1 or 2 or 3 or 4 or 5, can you earlier fix it if you do not do any kind of tweaking? No, you cannot fix it. So the outcome is not certain here. Second point is, can you fix the order? Can you guarantee that it will be 1, 2, 3, 4, 5 only? No, it is also not fixed. It can be in any order. And when these two things are true, these are true whenever you are trying to measure without tweaking any of the logic of the, like, qubits or the quantum gates or operations. So by default, this is the kind of outcome that you are going to get. So this is the overall thing. Now we will enter into the mathematics part of it. So I want to give a pause of 1 minute. I want to know if you have any doubt, because rest of the things we all will be doing. I have to write it. So if you have any doubt, you can ask. Okay. I will try to hide that one. Okay. So now we will be entering into that one. So I think by far you should be having a good understanding of the basis. There is no technical question, I guess.
Yeah, there is no technical question. Only one question regarding slides. Yeah, yesterday's slides we will upload. Today's slides also, madam will share and will upload. All the slides, all the handwritten notes also will be given to you. So please don't worry. Okay. Yeah. Thank you, ma'am. I think you can continue.
Yes. Okay. So now we will be taking everything, all the, like, fundamental things to describe a quantum state, quantum logic gates, quantum operations, and all those things. Okay, a superposed state and a basis state, everything. So firstly, the physical states that we have, the physical states, I'll try to be a little slow so that you can all follow. It shouldn't be a problem now. So physical states are represented by rays. Rays means a rays of light only, that thing, in Hilbert space. So what is Hilbert space? Hilbert space is a normed vector space. So it's kind of a vector space where we believe that the size, that is infinite dimensional, and it is a complete one. The complete one means anything, any quantum state you can actually represent in a Hilbert space. Is it a very kind of some real space that we try to refer, some memory or like that? No, it is a abstract model of representing the quantum states. Okay. And vectors are called, so vectors are called gates here. So what is a Hilbert space? A Hilbert space is a normed vector space where inner product is defined. Concept of inner product is defined. Now we again got another term, that is inner product. Right? What is it? We will look into that. But before that, there is another term called gate. So in quantum physics, we can represent everything using a notation. So the quantum state representation, or say representation, of quantum state, any quantum state, that can be a pure quantum state or a superposed or hybrid or mixed quantum state. How do we do that? For this thing, we use a notation that is called Dirac notation. Dirac is the name of the scientist, and we call it a Dirac notation. Right? This is alternatively also called as a bracket notation. This is the Kate that I referred. So we alternatively called it as there are two notations here. First one is the Bra notation and second one is the Kit notation. And together they are called a Dirac notation or a bracket notation. And how do we write that? We represent this Bra notation as this thing, this angular bracket and the straight vertical line. And the Kate notation is represented by this, a vertical line, then a right angular bracket. And definitely both of them are dual of each other. Vice versa. Okay, so they are a dual of each other. That also means we can represent this Bra notation as this thing, and we can represent the Kate notation as this thing. And this is the dual. There is another point here to observe, that is, the Bra notation is nothing but the row vector representation. Row vector means something like this: A1, A2, A3, A. So what is the size of this particular vector? It's a one row and n number of columns. So this is 1 cross n. Right? And similarly, this one is the column vector, that is a Kate, is the column vector representation. Where we write it like this. So what is the size of this particular matrix? Check here, we have n rows and only one column. So this is n cross 1. Right? So now we know, so we have introduced a few terms. First, we introduce that any physical state, which is a quantum state, that can be represented by ray or some vector in Hilbert space. Then we understood that what is a Hilbert space? It is a kind of a complete infinitesimal. Let me just mention that one as well. So it's an infinitesimal, infinite, infinite dimensional, and as well as complete. Infinite means I can, as if I want, I can increase the dimension as many as I want to or as required. This is the first point. See, this is very theoretical, but this is the representation. We are into computing, right? So we have to map the physics to the mathematics. And second one is a completeness. So complete means that if there can exist any quantum state, that means that definitely can be represented within that Hilbert space, right? And also another point is, in an Hilbert space, the inner product concept is also very well defined. What is inner product? We till now don't know that. But before that, we introduced another point, that is, any quantum state in Hilbert space or in any space can be represented or are represented using a notation which is called a Dirac notation. What is Dirac? Dirac is the name of the scientist who discovered it, and the notation is called as a bracket notation, where it is kind of a a combination of two notations. First is the bra notation, which is also the equivalently row vector representation of a 1 cross n form. And another one is the Kate notation, which is a column vector representation form in form of a n cross 1 matrix. And we have seen that the row vector, that is a bra, and the Kate, both of them are dual of each other. So alternatively, we can also write bra notation as this form, like Kate with a star on the top of that, and vice versa. Now, once we know this, now let us introduce what is an inner product. So, inner product is basically the bracket form itself. Meaning, meaning inner product of say two vectors. Inner product of two vectors, say psi and phi, in Hilbert space can be represented as, I will not be using the vector sign anymore, but this is the same thing. So they can be represented as phi psi. This is the inner product form. So you can see this is the bra. This also means, so this is the bra psi tensor product Kate phi. So writing these things is equivalent to writing this thing. Right? And now the psi with psi, that is greater or equal to 0 when psi is a null vector. Right? Now another very important point, combining the inner product and the direct notation. Let me tell you. I have told you that any like bracket notation or direct notation can represent any of the pure states as well as the superposed state. Now let us understand that how to do that. Say I want to represent a 0 in quantum. So classical 0 I want to represent in quantum. I will be doing it. I will be writing it in the Kate 0 format. Why Kate format? Whenever we will be doing the quantum gates, you will be understanding it. Basically, we always prefer Kate notation over bra notation because of the matrix multiplication compatibility. Okay? Because the vectors itself, the operator, the quantum operators, they are always in a form of a square matrix. So that means you can understand that it is something like n cross n. So if we use like bra notation to represent a quantum state, which is in 1 cross n format. So how that operator will be operating on some quantum state which is represented in the row vector form. So the matrix multiplication compatibility will not be there. Just to ensure that, we always prefer using the Kate notation over the bra notation. Right? Now, classical 0, if we have to represent it in quantum, we do it in this form, Kate 0 form. So this is not in a matrix form, right? So what is the matrix form of that? Please do focus here. These are all very, very important to continue any of the quantum thing, maybe tomorrow's class, anything that you have in QT03 and all everywhere. Okay? So this is a generic representation of Kate 0. We write it in this form, 1, 0. So this is a 2 cross 1 column vector. Okay? And this is a standard form. We always do this. Kate 0 is represented by a column vector 1, 0. What do I mean by that? 1 on this position means, says that it is the position. Let me write, it is the position for 0. So a high here, high or on, in this position signifies that 0 is on. So 0 is on is represented by a 1 on 0th position. And a 0 over here represents the same thing. So it is the position for 1, and an off here means 1 is off. Okay, and this is the fundamental pure state. Right, there is another fundamental pure state, which is, so this is for the classical 0. Now if we want to write classical 1, then it will be get 1, which is 0 and 1. So it is also a 2 cross 1 matrix, but just the reverse. Now you know that why it is 0 and here we have 1. Exact like the reverse logic. So this is another pure state. So if I say that psi is a vector which is a superposed one, or psi is in, say, superposition of logical 0 and 1, both, then how I can write psi? Psi can be written as alpha. What is alpha as of now? Don't worry about that. Some probability. Keep it simple. Alpha times Kate 0 plus beta times Kate 1. Okay. So again, for simplicity, alpha beta will be there. Simplicity. Otherwise, the normalization thing will not work. For simplicity, let me ignore alpha beta. So if psi is, say, Kate 0 plus Kate superposition, then how I can write this psi? Kate 0 is 1 0. Kate 1 is 0 1. So what will be psi? 1 and 1. So whenever something like this exists in a column vector form, where there are more than one is there, we have to understand this is a superposed state. And if it is with alpha beta, say alpha 0 plus beta 1, then simply it will be alpha 0 plus 0 beta. So it will be alpha beta. So it's so like both way you have to map, like from alpha beta, which is a 2 cross 1 matrix. You have to understand this is alpha Kate 0 plus beta Kate 1. So you have to be very like well versed with the kind of mathematical language that we use in quantum. Right? Now, so what we were talking about, we were discussing about the inner product space. And we then have again jumped to see the pure state representation of 0 and 1 in all form, like the Kate form as well as the matrix form. And also we have seen that what is the basic superposed state that we can get, which is a combination of 0 and 1 both. And we all have seen like all these concepts for single qubit. Only one qubit we have. Correct? So for 2, 3, 4, like more number of qubits, how to represent the states, we will look into that thing later. So this is the thing. Now, that means, say, I want to calculate the inner product of 0 and 0. Then we will do it for 1 and 1. And then we will do it for 0, 1 and also for 1, 0. We'll simply calculate it. You can also do it by yourself there. So this is the first one, say 0, 0. So this is nothing but this thing. Now this is bra 0, which is this one into this 1, 0. So this is a 1 cross 2 matrix and this is a 2 cross 1 matrix. So outcome should be a 1 cross 1. That is a single value. What is the value? It is 1 into 1 plus 0 into 0. That is 1. Similarly, let me do it for another one, which is inner product of 1 and 1. So this is 0, 1 times 0, 1. So this is also 0 into 0 plus 1 into 1, that is 1. So now the third one, any of these two we can take. Let me take this one. So say 1, 0. So this is bra 1, which is nothing but 0, 1. And this one is 1, 0, the ket 0. If you multiply it, that is 0 into 1 plus 1 into 0. So this is 0. That means you also have got another property of inner product. That is, the two similar product or similar vectors or quantum states, their inner product will always be exactly equal to 1. But if two states are different, then their inner product will be 0. Right? So this is another observation that we have got. So now, say the space is a linear vector space. So that means the psi and A, say phi 1 plus B phi 2. So there are two kind of vectors. This can be written as A psi phi 1, only the amplitude I can bring outside, plus B psi phi 2. Another observation is, let me just write in this way, psi and phi, their inner product star is basically this thing. Another one is, this is always equals to 1. The normalization. We have seen this. Okay. So now say the vector space. So what are we doing now? We are just dealing with the representation. Okay. In quantum setting. So now say the vector space is a d-dimensional vector space. So d-dimensional vector space spanned by the vectors or eigenvectors En, where n can be 1, 2, likewise it can be till d. Then psi can be written as sigma n alpha n En. Don't get confused with this. We already have seen this one, that psi is equals to alpha ket 0 plus beta ket 1. This is the same thing. Only the generic one we are trying to represent. So after this, there is another very important concept which is used in concept of this linear algebra and vector space, which is used in quantum, that is the orthogonal and orthonormal property. Orthogonal versus orthonormal. First, we will look into orthogonal. So two vectors, say u and v, are orthogonal to each other if their inner product is 0. Now by this we know what we mean by that. That is, this uv has to be 0. That means ket0 and ket1 are orthogonal to each other because inner product of 0 and 1 or 1 and 0 both are 0. This also means that, this also implies that u and v are perpendicular to each other. Okay. So this is orthogonal. Then what is orthonormal? So orthonormal vectors are those vectors for which first condition is they have to be orthogonal to each other. So orthogonality is the primary criteria for orthonormality. So they has to be orthogonal to each other. And second is each vector should have unit length. That is, their magnitude has to be 1. That is this thing. And what is this property? This is the property of normalized. So when normalized property applied on orthogonal, it becomes orthonormal. So that means orthogonal plus this normalization, they together we imply orthonormal. This is another very important observation. Let me give you one example, small example. Say in two-dimensional Euclidean space, where say u is this thing, 1, 0, and say v, vector v is 0, 1, then uv, this thing will be how much? It will be basically 1, 0 into 1, this 0, 1. See here, this was u, but this is the, like, everything here, vector is represented in the ket form. So this also means the 2 cross 1 ket. Whenever this is inner product of u and v, so I have represented u in the row vector form because this is bra u and this was ket u. Both are different. So this product is 0 and their length is also, they have unit length. That is u, their length, this is represented by this, is equals to v, and both of these is 1. And this is true, this condition is true for all vectors. That is u and v both. So what is the observation? Observations are u and v are orthonormal to each other. This is what our observation is. And this is an example for that. So if we have something like this, then say we have U as 2, 0 and V as 0, 5. So are they orthogonal? This is 2, 0. Dual of 2 is 2. Dual of 0 is 0. So there will be no change. 2 into 0 plus 0 into 5. This is 0. So therefore, U and V are perpendicular to each other. But the question is, are they normalized as well? Answer is no. Because this magnitude is 2 and V is basically 5. And both are not equals to 1. So we have to normalize it. Therefore, we have to normalize it. How we can do that? Just by dividing the vector with its magnitude. So U cap, the unit length for normalization, that will be U divided by this thing. And similarly for this one as well, vector V divided by vector V at modulus. But if it is in this form 2, 0 and 0, 5, then it is by default not normal in normalized form. So it is by default not orthonormal, but they are orthogonal. Okay. Now that we know what is orthogonal and what is orthonormal, and also let me give a quick recap, just a quick recap. So we started with the Dirac notation, the Hilbert space, the bracket notation. They are dual of each other. They are matrix representation. Then what is an inner product, which is a bracket form, and for a single qubit, how to represent a quantum state, for a pure state as well as superposed state. Then we have seen that the inner product calculations of a few things, and we have understood that if their products are same, like the states are same, their inner product is 1, otherwise it is 0. So, and from that we dealt into we were driven to the definitions of further axioms of these inner product and linear vector space. And after that we entered into, from all the definitions of inner product and all everything, then we entered into the definition of orthogonal and orthonormal vectors. So if their inner product is 0, that is orthogonal to each other. We also call that both the vectors are perpendicular to each other. And on that condition, if also the two vectors or all the vectors in the vector span given to us, if they are all normalized, then we also call it an orthonormal vector. So orthogonal property plus normalization or normalized property both together will form the orthonormal property. Then we have seen two examples, two very small examples, where it was normalized in one case, where in both the cases they were orthogonal, but in one case it was orthonormal as well, and in one case it was not orthonormal. Then we have seen that how we can normalize the non-orthonormal matrices. Now that we know these things, we will enter into the orthonormal basis, which is the fundamental basis for quantum mechanical postulates. Orthonormal basis. Orthonormal vectors we know. Now it's about the orthonormal basis. So orthonormal basis is a set of vectors En in a Hilbert space. So a set of vectors this in a Hilbert space is called orthonormal basis. If it satisfies two conditions. Condition number 1 is orthonormality condition, which is EM. What is EM? Like one of the members of this set of vectors. Okay, this is delta Mn, and this is equals to 1 if your M and N are equal, and this is equals to 0 if your M and N are not equal. The same thing from the inner product definition and all for the orthogonal and the orthonormal both, right? And the second condition is the completeness condition, which says that any vector psi in the space can be written as, let me write it here, psi is equals to, we have also seen this thing, alpha and En. How many such things are there? Of course, in n number of, where alpha n is En psi. We will see what it is and all those things. So they are expansion coefficients. So this is the formal definition of orthonormal basis. This might seems to be a lot more mathematical, but since we just covered the like single qubit state representation, so for single qubit or 1 qubit quantum system, orthonormal basis is a set of vectors. So this is the set notation, and the vectors are k0 and k2. Simple, nothing else. For a 2 qubit, it will be more. 3 qubit orthonormal basis will be more. So simple word, the maximum number of pure states that we can represent using those many number of qubits is what our orthonormal basis is. For example, let me just expand it to n equals to 2 number of qubits. Then maximum how many states we can have? Maximum number of states we can have is 4. Remember, this is maximum number of states. I may actually use less than 4, that is 3 states as well with 2 qubits, or 2 states as well with 2 qubits. But this is the maximum number of states possible. So what will be the state? 0, 1, 2, 3. Alternatively, we can write it as 0, 0, 0, 1, 1, 0, and 1, 1. Therefore, for 2 qubits, the orthonormal basis or the set of vectors spanned by this thing will be k 0, 0, 0, 1, 1, 0, and 1. Now let me gradually just tell you another form of writing this orthonormal basis as well, because in literature you might also be able to see those forms. So we will expand like this only. So say ket0, we know in a row vector, column vector form, it is represented by this, and ket1 is represented by 0, 1. Therefore, the orthonormal basis, it can be represented by this, or equivalently, we can also represent it by 1, 0 and 0, 1. It's also a set of vectors in a matrix form. Both are similar. Now, just like we have get 0 as 1, 0, where this 1 represents, it is a high for 0. Similarly, here, the orthonormal basis, can I write this thing that it can be represented by this as well? For 0, 0, it is 1, 0, 0, 0. For 0, 1, it is 0, 1, 0, 0. For 1 0 it is 0 0 1 0, and for 1 1 it is 0 0 0 1. So this is exactly the same thing, where this one represents it's a high for 0 0th. This one represents high for 0 1th. This is high for 1 0th, and this is high for 1 1. Okay. So till this point, I guess it is clear. Let me just little like continue. Then I will ask if you have any questions. So why? So now you should be able to understand what is orthogonal matrix, and orthogonal vectors, or a pair of vectors are orthogonal and pair of vectors are orthonormal, and then what is orthonormal basis till this point. And actually, what do we mean by, or how to realize orthonormal basis? Now, what is very important is to understand that why choose orthonormal basis in quantum mechanics. Why to choose this one in QM? So first point is quantum mechanics requires that probabilities are well defined. Then second one is that the measurements which was the expansion coefficient just mentioned, measurements correspond to projection operator. So measurement is required in quantum mechanics, and we got that from the orthonormal basis expansion coefficients theory. Third one is superpositions follow the linear algebra rules of orthonormal. Further continuation from point number 2, it can be like say 2.1. It is like the expansion coefficients alpha n have a clear probabilistic interpretation. And what is that interpretation? This alpha n square is the probability of finding the system in state En upon measurement. So what is alpha n? Alpha n is the probabilistic amplitude corresponding to measurement outcome of En, state En. Okay. So, assuming this En, this entire thing, is orthonormal basis, and psi is any state, any arbitrary state in the space, we can write, so it will imply that psi is this thing alpha n En. So any arbitrary state can be represented as one of the like vectors from the orthonormal basis with a certain coefficient of expansion, or which is also the probabilistic amplitude with respect to En state. Now if we take, say, taking inner product of both sides with draw En, so this will give En, we will be applying En on this side. So it will be En psi, and right hand side will be this, or say let me take Em. So it is Em psi, so this is Em, then here it is alpha n E. So alpha n we can take out, and sigma also. So this will be Em En. Now we know that if this is a set of vectors from the orthonormal basis and from the properties of orthonormality and all, so this is nothing but delta mm. So this is another kind of definition, and where this delta mn is basically 1 for m is equals to n, and for 0 if m is not equals to n. Therefore, on applying this thing, that is alpha n delta mn, the delta function, the delta will kill, or say will vanish, or yes, say will kill off all terms except for where m is equals to n. So the sum becomes alpha m only, because the sigma and remaining terms will be actually cancelled out. Let me take a small example for that. Say, what do I mean by this is, say, psi is a superposed state with alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. Now we know what are, like, which term is what. Okay. And you want to take an inner product with, say, E2. Therefore, E2 psi will be alpha 1. So E2 will be applied on all of them. So alpha 1, then E2 E1 plus alpha 2 E2 E2 plus alpha 3 E3, oh sorry, E2 E3. Now you know x, this one will be 1 and this one will get cancelled out, this one as well. So what we are left with for this one, see, if En is the state, then we are left with the amplitude alpha 2, right? So if EM is the state, M for say Bangalore, then we will be getting alpha M itself, right? Times this thing. So this will be what? So this is exactly alpha 2. Therefore, we can say that alpha N is nothing but En psi. This is called the projection of state onto the basis vector En. Alternatively, this is the component of psi in the direction of En. Okay. So alpha n is the component of the vector psi, which is a superposed state as well in the direction of En. Okay. So this is the thing. Now after these things, we will look into a little of the observables and operators. Okay, let me pause a little here and let me ask if you have any question. Just let me know. Uh, okay, any technical question till this part? You can let me know. I think, yes. So I hope right now it is second handwritten slide. What is a null vector? Null vector is a, okay, completeness is all okay. Okay, all clear. Okay. So by the term, okay, n and the number of states. Let me just go back. Okay, let me just take the questions. So completeness is 1, null vector was 1, and the relation between n and number of states. Alpha n explanation. Okay. 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 Let me go back. Yeah, let me start with the last one where someone asked about the alpha n explanation. So there are a lot of several interpretations of alpha n that we have seen. First one is we started with this thing. And where it is all coming? It is all coming from the orthonormal basis definition. Let me go back there. So after orthogonal and orthonormal, we have seen that completeness condition, it was that any vector that which is say psi, ket psi in the vector space or Hilbert space, that can be written in this form. So since any vector can be represented, and just remember the definition of that Hilbert space, it is coming from that same concept. Every concept is interlinked. That is why we are calling it as complete. Because if it is any arbitrary quantum state, it can be represented using some of the amplitude part or the coefficient part, as well as the projection of that particular psi in the direction of En. So likewise, any vector psi can be represented in this form, right? This is the first thing. Second is that what is alpha n? So alpha n, technically from the mathematical definition of that orthonormal basis, it is called the expansion coefficient. Then while we were discussing that why in quantum mechanics this alpha or these orthonormal basis things were used, then we have seen that this is nothing but alpha n square is nothing but the probability of finding the system in the state En on measurement. Okay, and alpha n, that is a square root of probability, is basically the alpha n, which we call as a expansion coefficient. This is the probabilistic amplitude corresponding to the measurement outcome of En. So the example can be given as this way. Say, I hope this math is clear to all of you, like what is alpha 1, alpha 2. I think at this math level, it is clear. So the interpretation of alpha, you can think it of in this way. Say, alpha is nothing but root over of, or say 1 by root 2, get 0, plus 1 by root 2, get 1. If I have only this way. So this is a ket psi. You can understand this. So what do I mean by that? It means that the probabilistic amplitude of 0, or it can be written as of psi to be in 0, is 1 by root 2. Therefore, the probability of obtaining state 0 on measuring state psi is 1 by root 2 whole square, that is half, that is say 50%. Similarly, the probabilistic amplitude of 1, that is of psi to be in 1, is 1 by root 2. Therefore, the probability of obtaining 1 on measuring psi is nothing but 1 by root 2 whole square, which is again half, which is 50%. So this is a clear example of, where is it? Yes. So this is a clear example of uniform superposition. Why uniform? Because the probabilities of two of the components are exactly equal. So this is a uniform superposition. This is all that we are referring to. So this is the coefficient, expansion coefficient or measurement coefficient, and the probability is the square of the coefficient. And the one who was asking null vector is all the vectors 0, nothing else. Just like the null matrix or something, which is no information basically. That is a null vector that I am referring. Okay. So I hope completeness and alpha and these things are clear. Okay. There were one more question, that is the n and the number of states. So before going into the observable, let me explain that as well. So see, in quantum, what was the fundamental unit? Qubits. So qubits are quantum bits. So the relation that we want to establish is quantum bits versus quantum states. So we'll do it in a very simple unitary method so that it's very clear to all. Say we have only one qubit. So we have a 1 qubit quantum system. That is, my system has only 1 qubit. So with that 1 qubit means what I can represent? I can represent either 0 or 1, or a combination of 0 and 1. That is, this is one pure qubit. This is one pure qubit. This is one superposed qubit, where this superposed qubit has two pure states as constituents. So it can be, your 1 qubit quantum system can either be initialized with 0 or 1, or a combination of 0 and 1. Anything. Have you got it? So for this case, one pure qubit where it is 0 only, it has one pure qubit and one pure state. Similarly, here it has one pure qubit and one pure state. And here it is one qubit quantum system, but its constituents number is 2. That is, this is a pure state, this is a pure state, and both of them are present. Right? So this is also one qubit, but that qubit itself is superposed. But that has two pure states in it. Similarly, let us do for 2 and 3, then it will be very easy. Say 2 qubit system. 2 qubit quantum system. What we can have in a 2 qubit quantum system? 2 qubit quantum system. That is one quantum system that has 2 quantum bits. Okay. So with that, what we can represent? This says that maximum number of states that can be incorporated is basically 2 to the power 2. This is the number of qubits. That is 4 states. So what will be the states maximum possible? They can be 0, 0 or 0, 1 or 1, 0 or 1, 1 or any combination of them as well that I'm not writing. Or it can be psi is equals to alpha 1, 0, 0 plus alpha 2, 0, 1 plus alpha 3, 1, 0 plus alpha 4, 1. And if any quantum state is represented in this form, then we call it as a superposition. So psi 2 is one quantum state which is in superposition of 2 qubits or 4 states with coefficients alpha 1, alpha 2, alpha 3 and alpha 4. This is the interpretation. I hope now you know that if it is 3 qubit system, that maximum number of states that you can incorporate is 2 to the power 3, which is 8. So the best combination of encoding that you can have is all 8 states together in a superposed state. So then psi will be one quantum state which is in superposition of 3 qubits, that is maximum 8 states with coefficients alpha 1 to alpha 8. And states will look like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So individually all are pure states. Together when they are is in superposition, so they create one superposed quantum state which is psi. Okay. I think the doubts are clear. And we do not have time for the observables and operator. It will take 20 or 15, 20 more minutes of time. So let me pause here. And now if you have any more question, you can ask. Otherwise, I think we are good to go. Mixed state is the superposed state. Mixed and superposed, they are similar meaning. Yes, we will look into the block sphere representation of that, the multi-dimensional representation for n qubits. Just before like next class, yes, all the writing that I have done, that will be incorporated in the lecture notes. I have kept them all the things for the first one as well, and for this one second, all the sessions you will be getting everything. Don't worry. Just do a good revision of the whatever we have learned in the first two for the third one as well.
Yeah, for participants' information, the slides of yesterday's lecture have been uploaded. Madam will share now in some time. We will upload the second lecture slides also. Yesterday's video recording is also uploaded for those who have missed, or for those who want to revise. You can again go back and listen to the video. So there is no problem. So every day after the class is over, the video will be uploaded, and Canvas is updated. Please check. All of you must have received the invitation. Please check that also. We have sent invitation to all those who joined till 3 o'clock today. Okay, please check. Yeah. Thank you so much, ma'am, for your valuable time. I think ma'am has left.
No, I'm here, sir.
Okay. Your screen is shown. Okay, sorry. Yeah.
Okay.
Suddenly I like. Yeah, your appreciation is going on, so you can.
Okay.
Please.
One asked one question, that is a 1 qubit state. Is it in superposition? Yes, it was also in superposition or mixed state. If it is represented like gate 0 plus gate 1.
Yeah, for those who have not received Canvas invitation, please message on fdp.academy@mnit.ac.in. We are answering some of your questions. Those who have joined at 3:30, okay, we are sending after around 5:30 or something, we'll send all the Canvas invitations. Right, another 30 people have joined. So totally the strength has increased to 750 or something. 700 plus is the number now. So hopefully they will all join the WhatsApp group also, and we will open the WhatsApp group for discussion. If there is anything missing, please let us know. But I will request all of you to read the chats of the previous chats, what happened, right? Then those questions you can answer, right? Some of your questions may have already been answered. If you are repeatedly asking the question again and again, others will get disturbed, right? So there are 500 people, so you must value their time also, because they want to see if something important is missing or something, right? So whatever questions you ask, please first read the chats that are happening in the last maybe one day, and then you can ask the question if it is new. If somebody has already answered, so you can check that. Yeah, those who joined exactly around 3 p.m. or after 3 p.m., maybe 2:30 or something, I moved out from there till 2:45 or something we have sent. So anyway, we will open the WhatsApp for chat now. You can question the things, right? Unverified is you should use your login to login. Okay, you have to use the registered, what is that, registered number, right? So WebEx also, please try to receive the WebEx login and join from that. And same is the case, register on the WebEx. I have sent PDFs of WebEx, how to join WebEx and how to join Canvas. Actually, what we want to do, we want to simplify things, which is difficult. Please follow those instructions. They're very simple instructions. If you follow the instructions, there is no problem. You can immediately join. But the point is, we want to click and join. It is not possible because we want to log the attendance. You don't have to submit another form is not to be there. Google form is not given to click the attendance. You don't have to do that. WebEx automatically maintains attendance, how many minutes you are in the class, right? So you can, that's how we are doing that. So please maintain that attendance. That is what is important, right? So you can ask the same questions in the mail. Ma'am has explained each and every point. Yes, that's good. Yeah, those who have not received Canvas invitations, you can please check. Few of you, I think 8 or 10 of you have not received. We are trying to send again. But otherwise, there is no problem. You can do that, right? Thank you so much, ma'am. We will meet at 3 o'clock on Monday. Yeah, कर दो 3 बजे कर. Close the YouTube कर. YouTube बंद. Yeah, participants, we will open the chat. So please go to the chat and ask questions. But before you ask the question, check whether your question has already been answered, right?